Okay, folks. So getting into the discussion on quantization, pretty much everything you see in front of you is waves. Waves, the course is on waves, and waves permeate everything. Waves permeate, like, I mean, with light being both particle and wave, and then the Broglie's hypothesis saying the particles are also waves. You get into, you know, the way I'm talking to you now, the waves are going from me to you, sound waves, and then the way you're seeing things is light waves, and there is, you know, waves permeate the devices that you know, interact with. At the heart of everything that you look at is, you know, whatever, this board, is like, you know, there's vibrations in there. Things are moving. Things are, you know, electrons are orbiting or whatever they do. And whenever something moves, it has mass, it's got a wavelength associated with it. So the wave-particle duality is essential in our understanding of the physical universe. Where that started was back in the day, there was something called the Blackbody Radiation. You have a box, you heat it up, and I don't know, whatever, like a caricature, it would be like a hole here, and a little light fire here, and you measure, look at the radiation coming out of this light, and you measure the power as a function of wavelength. So you have, I don't know, you have yellow and red light, and, you know, whatever it might be. Let's say you have light coming out, you know, they don't. But let's say you have radiation coming out, and you look at the wavelengths coming out, and how the power is distributed among the wavelengths, and that depends on the temperature. You end up with, let's say, power versus lambda. You end up with a graph that looks something like this, okay? And our understanding of the universe, you know, is one of the key things that we take pride in. Our ability to master and control and shape, but it begins with understanding. The more we, you know, the more stuff we understood, the more able we were to create with it. When Faraday and Maxwell were doing their work, nobody would have thought that we'd be able to use it for we're using it now. Developments associated with Schrodinger and de Broglie and Heisenberg and whatnot quickly found application. There are discoveries in physics that didn't come into play until much later, when engineers were able to apply them. And something to consider, that a lot of things that we look at and play with might not come to fruition in terms of actual physical applications or big physical applications until some creative being comes and, you know, puts them into application. But the idea of understanding the physical universe that we live in is key to our nature. So I take you back a little bit, you know, a few centuries before, when Newton decided to, you know, to go from, if you're trying to find the area under a curve, what you did before was find, I mean, the way he did it before he came up with integration was he had to do sums, you had to do summations. Things where you had this plus that plus that plus that. He came in and said, oh, heck, it's taking too long. I'm just going to replace the sum. Let's say you have function f, and this is delta x. And he said that the work was equal to more or less the sum of f delta x. So what you're doing is really adding rectangles in here. He said, heck, let's take it too long. Instead of doing that, let's just do, that's going to take me 4, 5, 6 hours. And if you do that, you're missing out on these bits. You have to break that up again, and then you have to break that up again, and hopefully by third or fourth breakup you get to within 99% of the result that you're looking for. So it's only approximate. So he came and said, heck with it. A, it's taking too long. B, it's not, you know, it's not even accurate. So let's just save ourselves the hassle and do integrals. So integral of f dx, that will give us the work, and we're done. Okay. So went from chunky and rough, kind of you know, edgy, to nice and smooth. Right. This was discrete. This is continuous. Things became very continuous and nice and smooth. Right. After Newton's laws, after Newton's integration of, you know, calculus, and after the introduction of calculus, differentiation and integration, Leibniz too, things became smooth. The way he had a huge impact on the way things developed. There was the action reaction, checks and balances. There is the idea that things are nice and smooth and continuous and harmonious, and there was a book, look it up, called Harmonices Mundi, Harmonies of the Universe, how everything is nice, and that had a huge impact on the classical era as well. The classical music, things are nice, and they move in rhythms. There are harmonies to the universe, the celestial objects and whatnot. Okay, so things were nice and good until we came up with this graph in the 1800s, late 1800s. People were looking at the blackbody radiation, and they'd like to be able to, can we model? Can we understand this graph to the point where we can model? If we understand enough about physics, we should be able to, model this graph. And what happened was they were trying to model this using equations, theoretically come up with this graph that they saw, this is collected experimentally, and they were able to fit this part okay and that part okay, and there was something funny going on here they couldn't do. Bugged them down for a long time. They were not able to get anywhere. That's the idea of the blackbody radiation. Take a look at it until a guy killed. Maybe we got Planck, who got the Nobel Prize for this. He came and said, we've been bogged with this for a long time, and the only thing I haven't done, we've tried everything, we've done everything we can, the only thing I haven't done is go back we've taken things for granted. I haven't gone back a few centuries to look at what happened there. Maybe there's something there. Maybe we shouldn't do integrals. Maybe we should do summations. And he did put summations in that. Well, energy is not something like, let's think of a liquid as a continuous thing. You can't just add as much as you want energy or anything into a cup. You can only add it in chunks. And the chunks are pretty small, but they're chunky. It's not continuous. So that's what he did. That recognition on his part, that cognition on his part, allowed him to fit this appropriately. But that took us from the harmonious and the continuous and the melodious to the chunky and edgy and corpuscular, stepwise, or the discrete. That was like, we just left this summation business to go to integrals, and that's what we've been doing for so far. We did really well with this stuff with continuum mechanics and classical mechanics and a whole bunch of stuff. I think it's fine. And now you're telling us that we should not be using this anymore. If we want to understand the universe at a deeper level, there's a big kind of a wake-up call for people. So his idea was, this is not exactly, you can look it up. His idea was that things that were in here, like, he said there were springs. Not springs, not springs sticking out, but everything is springs. Everything, because of lattice dynamics and lattice structures and whatnot, everything can be approximated more or less as, like, if I bang this thing here, there is vibrations that travel. And you can say that this is made up of a bunch of springs, and you can change the spring constant to make it more stiff, so you can model a lot of lattices and crystals with springs. So that these springs that exist here are such that, the energy of these springs is quantized, okay? Quantized means that the energy of the spring does not change from, so we're talking about not springs that stick out of the wall, but we're talking about, springs being everywhere in the box, right? These springs or lattices or, the vibrational energies of these spring-like things is quantized. The vibrational energy is quantized, and you can only add energy in chunks. You can't add it continuously. Okay, that was 1900. And 1905 came Einstein and said, not only the lattice vibrations are quantized, but the actual radiation that comes out of this is quantized. And that was a huge step forward. That was the birth of, depending on which perspective you take, that's the birth of quantum mechanics, because 20 some years later, so what he said was basically that, we'll talk about the photoelectric effect, but one of the results that came out of Einstein's discussion is that, light has no mass. Light has no mass. And later on, he came up with general relativity, which was phenomenal. Light has no mass, yet it bends around, it bends in, it bends around gravitational centers or centers of energy mass. So you have light going in certain, funny paths around objects that have high gravitational interaction or a high energy concentration. It could be electromagnetic energy or whatever. So yeah, everything interacts via the gravitational interaction. This guy, so he said that, well, light has no mass, but it carries momentum because it carries energy. So the momentum was equal to P is equal to H over lambda. And he said that the energy of a photon, light is, both light and particle, energy of a photon is equal to P times C, okay? So hc over lambda is what you see. Energy of a photon is hc over lambda, okay? So from that came, 20 some years later, came de Broglie and said, well, light, just because it's a particle, just because it has no mass, we call it a particle and a wave. That's not fair, kind of. And he submitted a shortish thesis to his committee, saying basically that, well, my thesis is the following. All I'm going to do is, here's my thesis. My thesis is, look at this. This is P equals H over lambda. You're saying that, Einstein is saying that light has wavelength and it has momentum. And just because light has no mass, it's not going to be treated special. And, we're not gonna give it a special status as opposed to other stuff. It's not fair to say just because it has no mass, it has this dual nature. We're going to say that we're not going to give it special consideration. I'm going to say that, okay. I'm going to say that, okay. His hypothesis, I think he had one equation. He says lambda is equal to, he said lambda is equal to H over P. He said, okay. He said, it's not fair that just because light has no mass that we treat it as particle and wave and not extend this treatment to other stuff. Anything that has, he did this, and his committee was like, oh my God. Like, they understood the implications of this rearranging of the equation, in that now anything that has momentum has a wavelength. That was de Broglie's hypothesis, and he got the Nobel Prize for it shortly after. So the committee was not sure about this business of simply rewriting Einstein's equation for light, P equals H over lambda, to lambda equals H over P. They understood what it meant, but they're like, wow, this is going to open up a huge door of what, say, like, we got lambda is equal to H over, now any object that has mass and velocity has momentum. We've gone from light, which has no mass and carries energy, thus it has momentum, and momentum of light is seen in its ability to carry energy that has no mass, to saying now that anything that has momentum has a wavelength. They're like, this is big, let's check with somebody on this. They sent it to an external who happened to be Albert Einstein in New York, and he said this is the greatest thing ever. So they gave him the PhD, and he got the Nobel Prize later. He was vindicated basically by what? Well, how do we know that light is a wave? We know that light is a wave. So this guy is saying that all matter is a wave. Electrons have mass, and light has no mass. Right? Yet electrons and protons that have mass have a wavelength. How do you show this? How do you show that light has a wavelength? How do you show that light is a wave? How do you show that anything is a wave? Well, the one way we show that anything is a wave is interference and diffraction. So you have a wave coming in, and this is a wave at C. These things become secondary sources of waves. These holes here in the water break, in the wave break. Well, I mean, what is diffraction? It's like, can be thought of as interference from multiple sources within the slit width. So this is waves at sea. These become secondary sources, and they interfere. And you can look at the maxima and minima, maximum minimum lines, and if there was a source of light, you would see an interference pattern here. So how do you know that something is a wave? It's because when you have a wave at a trough, and wave at a crest and a wave at a trough, and they meet, right? They cancel each other out. And if they meet such that you have 2 at a crest, you have constructive interference, you have twice the amplitude, you have 4 times the intensity, and if they are out of phase, you have 0 intensity, and you have destructive interference. So the way you show that something is a wave is by interference and diffraction. If there is diffraction and interference, you know that it's a wave. So basically you have waves at sea that are interfering and diffracting, and that's, you know, that's what waves do. Now what do we have with light? Well, we have with light, we have the same thing. We have, you know, if you send light through a double slit apparatus, double slit aperture, you got, as we saw from the realistic description of the double slit, we have, we have this thing here. We have the interference effects as fringes, and we have the slit width effect as the diffraction envelope. Yet, now, if we have just a single slit, we send light through a single slit, right? What are we going to have? Well, we're going to see if you have a single slit here and you have a light source here, what happens is, remember our discussion of Rayleigh Criterion, that light becomes, when the source, right, sends waves through here, and they form a diffraction pattern on here, and, you know, the source here looks like a big envelope at your retina. That's how much space it occupies. But the idea is that if you send light through an aperture, you'll see this. Now, if the aperture is circular, okay, we're looking at a 2-dimensional representation of the intensity profile, the diffraction envelope. So this is really intensity. It's more intense here than there. So what you end what you end up seeing is light that is more intense here than there. You don't see something like that. You see a band, right? However, if this aperture is circular, what you end up seeing is, I mean, think about it. You'll see this is now in 2D, and what you end up seeing is circular aperture. The intensity is bigger here than there. So what you see is rings. You see a ring with decreasing intensity until you get to here. You see, you know, a bright disk in the middle, and then rings subtending or going around the rings around the central diffraction maximum. You have a high intensity disk like that, and then rings around it. Right? So bright, dark, and this is your diffraction pattern. Diffraction. This will be the dark part, dark ring. This will be the bright ring, and so on and so forth. So how do you know that light is a wave? This is an excellent way of showing that light is a wave, because that's what waves do. We know light is a wave. You know, you send the laser comes through, goes through the aperture, and forms a diffraction pattern. So we know that light is a wave, and it does this. Anything that does this is a wave. So what happened after de Broglie's hypothesis is that people ran electrons through an aperture, electron beam through an aperture here, and they looked at the intensity profile on the screen, or on the, no, not screen. They detected the intensity profile a certain distance away, and it looked exactly like that. And the only thing that does this is a wave. So that was proof, vindication for de Broglie that he was right. That matter, electrons, neutrons, protons, whatever, are both particle, and matter is both particle and wave. That was a huge discovery. Now, let us talk about waves a little bit more and see where this led. Right after de Broglie, we have the wave equation. Well, the wave equation for waves on a string is y equals y naught sine of kx minus omega t. And S equals to S naught cosine of kx minus omega t. And then you have light. Light, well, E or B equals to E naught sine of kx minus omega t. You can add a phi if you want. And what is this telling you? Light is a wave. And, you know, what we got here is something really interesting in that, you know, light is both particle and wave. And it's described by a wave equation. We know it's particle from Einstein. We know it's a wave from Young's double slit experiment from Young. Right? So light, which is a particle, is described by a wave equation. And what happens here is if you take the square of the amplitude, what do you get? Well, let's take a look at this. If I take the square of, you know, what is the intensity? What is power? Power in a wave is equal to 1/2 rho v, 1/2 mu v omega squared y naught squared. And intensity is equal to 1/2 in a sound wave, 1/2 rho v omega squared S naught squared, S max squared, and so on and so forth. And by the same token, the intensity of light is proportional to, so what do we see from here? Now, keep in mind that intensity is nothing but power over area. So they're related. So you know, when it comes to light, then we notice that, or we deduce that, we conclude that intensity is proportional to the square of the amplitude. And with light, the same thing. Intensity is proportional to the square of the amplitude. But what does intensity mean for light? The more intense light is, the more photons you have in a certain region. Like, so intensity in terms of sound means more power. Like intense sound will maybe put a hole in your eardrum. Right? What does intense light mean? Is that there is a lot of photons in the light. You can see more stuff. There is more light. There is more photons in the area. Intensity corresponds to brightness, if you want. Right? So this is a hint of what is to come. You'll see that in a couple of minutes. But for now, you know, I was in second year, and I was telling people, okay, well, we have this equation that describes light, and there is something interesting here in that, look at this. Focus on this part here. Right? What is K equal to? K is 2 pi over lambda, and omega is what? 2 pi f. And look here, that is hc over lambda. Hc over lambda, c over lambda is what? V over lambda is f, so it's equal to h mu. In physics we like to call frequency mu, but really it's nothing but h times the frequency. So Planck's constant multiplied by the frequency gives you the energy of each photon. The energy of a photon is equal to hc over lambda, or hf. This is telling you that the more energetic the photon is, the higher the frequency the photon has, the more energetic it will be. So what we have here then is from Einstein, okay, we have something that is a particle described by a wave, but yet here what do we have? Look at this here. Look, this K is 2 pi over lambda. In physics, constants are nothing. We don't care too much about them. But the form of this, look, K is 2 pi over lambda. Can you relate this to anything over there on that board? Can you relate this to anything on that board? Think about it for a second. This is the energy of a photon looking like that. What this is telling us is that K is the wave vector or wave number, 2 pi over lambda, something over lambda, something over lambda. It's nothing but momentum. This is the same as that, just a constant or two off. This is phenomenal. In that this is the momentum of the photon, or something that relates to the momentum of the photon, just a constant off. It's really the momentum of the photon. And this is nothing but omega. Omega is 2 pi. F is related to the energy of the photon. This is the energy of the photon. Constant here, constant there. The gist of it, the bottom line, right, the pay dirt, is that this is momentum and energy. So I was in second year, I was looking at this stuff, looking at de Broglie's equation. I was like telling my classmates, oh, look at that, guys, this is phenomenal. This equation describes a particle, right? Describes light as a particle from Einstein. Yet we have this guy saying that, things are both particle and wave. Like, okay, if we can use this equation to describe a photon, which is a particle in wave form, is there an equation that can describe a proton or an electron or neutron, which is a particle in wave form? Because de Broglie said it's not fair for light, just because it has no mass, to be called particle and wave, and not other things, just because they have mass. Right? So I'm like, we're so close. There's got to be a way to do this. There's got to be a, I should be able to, come up with something that maybe looks like that now, right? Something like this, and sine of, this is a simplistic way of saying it, sine of, I'll put, this is nothing but the momentum. Remember, K is 2 pi over lambda. In physics, constants are nothing, crap, for the most part, but this is something over lambda is momentum. So I'll put the momentum of the particle here, I'll put the energy of the particle there, and I'll multiply this by x, multiply by t, put a minus sign. This is a very simplistic way of saying it. And this thing, which while E squared describes the number of photons in a beam or a certain area, I'm going to have something that if I square it, let's say, it'll give me the number of particles, like protons or neutrons or whatever in a certain area. I'm like, if we're able to use this equation to describe light, which is a particle in waveform, there's got to be an equation, just because if we agree with de Broglie that matter is both, an electron is both particle and wave, there's got to be an equation that describes the electron in waveform. It's going to be similar to this, momentum and energy, and there's going to be a way to do it. They said, yeah, there is a way, and for sure there is a way, and somebody beat you to it by 40 years, and his name is Schrodinger. Right? So I was so excited that now I can, plug this in there, and then, of course, I know about the Schrodinger equation. I just didn't know about this connection between, the wave equation and de Broglie, and this is missing in a lot of discussions on quantum mechanics. So I was so excited. I'm like, there's got to be something that describes. Guys, we're so close. We can just do this. Put momentum here, there. Yeah, Schrodinger beat you to it. This is a simplistic form. Of course, the complex form is what you use. And psi squared or psi star psi, more or less psi squared. Okay, that gives you in one interpretation, it gives you the number of particles in a certain area. In another interpretation, it gives you the probability of finding a particle in a certain area. But after this, it was a piece of cake. It was like, the work was done by de Broglie in making this huge leap out of nowhere. Like he says, just because it's not fair, it's got to be, there's no evidence. The evidence came after. So all these big leaps in physics came seemingly out of nowhere. There was no mathematics to support them necessarily. Right? So Maxwell did something similar. Einstein did something similar. Right? So it's not necessarily that mathematics will get you there. There is some other source of stuff that comes in, and you have to tap into that somehow to come up with you let your imagination and creativity. Look at how Einstein was sitting looking at a clock once and looking at light and realizing something phenomenal about special relativity. Right? Some of the amazing discoveries in physics came not from math, but from something else, some sort of creative center somewhere. Right? So this is a story. So after that, we have Schrodinger's equation, which laid the foundations of all of quantum physics as we know it. We're able to, just about everything you do today has got something with, quantum device, semiconductors, whatever. We're gonna pause now and continue with the rest of